This time we will go through a node voltage problem, but with a current source instead of a voltage source. Note how the steps are the same, but the givens of your problem change the resulting math. Again, as a reminder, a voltage source defines the voltage at its terminals, but you have to perform a full circuit analysis in order to calculate the current drawn from the source. A current source defines the current in its branch, and you have to perform a full circuit analysis to calculate the voltage at its terminals. KCL is the current flow expression of conservation of charge and states that the sum of all the currents going into a node is equal to 0. KVL is the voltage expression of conservation of energy and states that the sum of all voltage drops around a closed loop is equal to 0. So let's set up an example with a current source. Take the time to observe your circuit. You have three resistors, R1, R2, and R3, connected in a specific configuration. Generally, in a circuit, you would be provided with the values of the resistances of each resistor. Each resistor corresponds to a voltage drop in your circuit. You also have one current source. Each source represents a known quantity. In this case, the current source provides you with the magnitude and direction of the current going into node A. In general, the reference point or ground will be provided, but if it is not, remember to select a convenient point in your circuit and dub it ground. So let's provide you with some known quantities so that we can go through this example in a methodical way. I1 is equal to 5 milliamps, R1 is 10 kiloohms, R2 is 5 kiloohms, and R3 is 5 kiloohms. In step 1, identify and name the nodes. In this instance, that has already been done for you. Then draw currents according to the convention. Note that the currents are drawn going from left to right in the horizontal branches and top down in the vertical branches. The naming convention, for example, for current IAB, is the current going from A to B, so the name as well gives you the direction of the current. In the case of IB1 and IB2, both of those currents go from node B to ground, so they only have one subscript, one letter subscript. But because they are two separate branches and in general will have two different values, I separate them by naming one IB1 and the other IB2. Now you need to draw and label the voltage drops across each component and make sure that the polarity of these voltage drops is consistent with the direction of the current. If the current is going from left to right, then the positive sign, the positive polarity has to be on the left and the negative on the right. Note also that you know the current flowing into node A, IA, which we named in that convention because it is the current going through branch A into node A. IA is equal to I1. Again, let's review how we use node voltages in order to express the relationship between the voltage drop across a resistor and the current going through a resistor. If we take R1 in the circuit as an example, the current through R1 is IAB. The voltage across R1 is VAB, but I can actually express it as a difference between the voltage at A, between the node voltage at node A, and the node voltage at node B. So VAB is equal to VA minus VB. And so the Ohm's law expression for the current going through the resistor R1 is going to be IAB is equal to VA minus VB over R1. And it's this expression that we are referring to when in the instructions we tell you use the node voltage expression for Ohm's law. Now you can only apply this expression to the resistors in your circuit. Do not try to apply this expression for any of the branches that contain a source or any other kind of component. So continuing from the review of the node voltage expression for the currents going through each branch, we write KCL at nodes A and B. KCL at A is I1 minus IAB is equal to 0, so I1 is equal to IAB. We will actually use this in the second expression. The second expression is going to be KCL at node B. IAB minus IB1 minus IB2 is equal to 0. For currents going through the resistors only, we're going to write Ohm's law expressions in terms of the node voltages, and we're going to replace these expressions into the KCL equations. For the time being, I'm not going to write IAB in terms of node voltages because I actually know what the value of IAB is. IB1 is equal to VB over R3 and IB2 is equal to VB over R2. So for the second expression, the KCL at node B, I substitute everything I know, as much as I know, and review the final form of the equation for KCL at node B. And this expression shows that I now have an equation where I only have one unknown, that's VB. So if I gather what I know, I1 is equal to 5 milliamps, R1 is 10 kilo ohms, R2 is 5 kilo ohms, and R3 is 5 kilo ohms, and I substitute into the equation from the previous page, then I have a final form where I can solve for VB, and so VB is equal to 12.5 volts. Now you can calculate the rest of the voltages and currents. So again, we know the value of IAB from the source, and I don't have VA. So in this instance, I'm actually using the node voltage expression for the current IAB in order to calculate one of the node voltages. IAB is VA minus VB over R1, and so VA is equal to 62.5 volts once I complete my solution. In addition, I can calculate the currents going through the resistor R3 and R4 and R2. IB1 is equal to VB over R3, so IB1 is equal to 2.5 milliamps. IB2 is also equal to 2.5 milliamps because R3 is equal to R2, and VB is the same, obviously, across both resistors. I can also solve for all the voltage drops. VAB is equal to VA minus VB, so that's equal to 50 volts. And then I take the time at the end to write out all my results in one spot.